You're back. Good, good, good. How's everybody doing? Again. How's everyone doing again? Over and over again. This nightmare of us keeping getting kicked out is annoying. Y'all have a good Labor Day weekend. Not really, because I had to work on Monday. They don't treat us teachers right. They made us go to work. Yeah, what kind of Labor Day is that? Huh? It's not any kind of Labor Day. I had to labor on that day. A day of labor. Yeah, honestly, I sound like I'm complaining, but being busy and working is better than being bored and whatnot. I'd rather be occupied than unoccupied. So back to this concept. This is how the notion of this cube root got invented, because they thought to themselves, what mathematical entity could we invent such that when we multiply it times itself 3 times, you get x? And that's precisely the cube root. The cube root of x is precisely that value, because when you multiply the cube root of x times itself 3 times, that becomes the cube root of x itself cubed. And that ends up becoming x. And it's just a consequence of adding fractions and powers. I don't get why teachers don't explain this stuff, because I remember learning math and them talking about square roots and cube roots, and I was thinking, why is this stuff even important? I mean, who even came up with this, and why is this stuff even important? Well, it's important because of these elegant connections that I'm revealing to you. I forgot who asked the question. Someone asked the question why, when we say x raised to the m over n, that the denominator becomes the amount of roots you take and the numerator becomes the power. And this is why. More interestingly, if you have an example where, let's say you don't have a 1 in the numerator, what about this right here? X times x raised to the 2/3 power times x raised to the 2/3 power. Notice this gives me x raised to the 4/3 power, but that's not a whole number. So what if I were to do it again? That's x raised to the 2/3 power. So that's 2/3 plus 2/3 plus 2/3. That's 6/3. So that's x squared. So now it finally breaks down to something called x squared. So you're saying to me that this is an entity such that when you multiply it times itself 3 times, it equals x squared. So, well, that's precisely the cube root of x squared. Because only whenever you multiply the cube root of x squared times itself 3 times do you get the cube root of x squared cubed, and cubing a cube root leaves you the inside. So this is where this concept got invented. Have I satisfied your question when we were asked that? Very good. Yeah, Jay, that's why cube roots and square roots and this whole thing got invented because they found these patterns. The ancient mathematicians thousands of years ago found these patterns, and so they decided to create a mathematical formalism that defines x raised to the m over n as such, because it correlates to these mathematical phenomena as we see here. The ancients of math, yup, and now we're the moderns of math. So, now that we're experts on this stuff, let's solve a problem like x raised to the negative 2/3 is equal to 5. What is x? Well, to solve this problem, I will have to remind you of a property that I've erased, and I'll put it in yellow. X raised to some, actually, we could say m over n, raised to some power p, that is equal to x to the m over n times p. So don't forget that. So we're going to apply that over here to help us solve for x. We can't solve for x unless we have x all alone. And we can't solve for x unless that power of negative 2/3 goes away. So what we can do is raise both sides of the equation to the negative 3/2 power. Why is that? Well, notice what happens on the left-hand side. I'll get x to the negative 2/3 raised to the negative 3/2. Okay, but that's the same thing as x raised to the negative 2/3 times negative 3/2. And that will equal 5 raised to the negative 3/2. Okay, but notice the negatives cancel because negative times a negative is a positive, and the 2's cancel and the 3's cancel. Everything cancels. Everything cancels to give me 1. So it's x raised to the 1 power, which is just x. But that equals 5 to the negative 3/2, or negative 3/2, yeah. So we're done. We just solve for x. Then one might ask, well, what is 5 raised to the negative 3/2? 5 raised to the negative 3/2 is the same thing as 1 over 5 raised to the positive 3/2, which is the same thing as 1 over the square root of 5 cubed, which is the same thing as 1 over the square root of 5 squared times 5. That's equal to 1 over 5 root 5. Rationalizing, if you'd like, is equal to square root of 5 over 5 times 5, which is root 5 over 25. Any questions? Let's do another one. what about negative 2x raised to the negative 1/2 power? No. Let's say raised to the negative 3/2 power is equal to 4. Okay. How do we solve this guy? We want to know what x is. First we divide by negative 2. You get x is equal to a negative 3/2, and that's equal to a negative 2. Then we know what we have to raise both sides. We have to raise both sides to the power, the reciprocal of this, negative 2/3. Because when I multiply this negative 3/2 times this negative 2/3, they cancel out to give me just positive 1, and that's the power and the x. So I get x to negative 3/2 raised to the negative 2/3 is equal to my negative 2 raised to the negative 2/3. But that's equal to x raised to the negative 2/3 times negative 3/2. So that's equal to x. Bringing the calculation over here, that means I have over here a negative 2 raised to the negative 2/3 power. That's the same thing as a negative 1/2 to the positive 2/3 power. That's the same thing as a negative 1 all over the cube root of 2 squared. Okay. Which doesn't break down. The cube root of 2 squared doesn't break down to anything more simple. So that's our answer. Our final answer is this, or we could have stopped right here. Both of those answers are equivalent. Any questions? So what if I have something like this? 3x to the 3/4 is equal to x to the 1/2. I want to solve for x, okay? So I'm going to have to raise both sides to some power in order to do so, okay? So in order to figure out why the power I'm going to choose works, let's rewrite this x on the right-hand side. I'll just reproduce what's on the left-hand side, but let's rewrite that as 2/4. How did I get that? Well, I just multiply top and bottom here by fancy number 1. And so they have a common denominator here. Why do we even wish to establish a common denominator? Oh, well, it's because this is going to allow us to solve for x, okay? Notice that if I subtract this term, I get this. So notice that I can pull, oh, this should say 3. Notice that I can pull out x to the 2/4 because that's the lowest amount. I can pull out x to the 2/4. Remember, if I pulled out an x to the 2/4, this term just becomes a 1. Well, what happens to this term? Well, it's a 3x to the 1/4. How did I get that? Well, when I redistribute this x to the 2/4, when I redistribute this x to the 2/4 and it hits that 3x to the 1/4, the 2/4 plus the 1/4 gives me the 3/4. So then I can reestablish the equation. I can restore the original equation above. Why is it helpful that I did this factoring process? Well, it's because of the zero product rule. I can set this piece equal to 0 and that piece equal to 0. So x to the 2/4 is equal to 0, and separately 3x to the 1/4 minus 1 is equal to 0. Over here, this implies that x to the 1/2 is equal to 0, which implies that the square root of x is equal to 0. So I can square both sides, and that implies x is equal to 0. Well, that's one of our roots. Over here, I add a 1 to both sides. So I get this. Then I divide both sides by 3. And I get this. And then I can raise both sides to the 4th power. So I get x to the 4 over 4, which is just x to the 1, which is just x, is equal to 1 over 3 to the 4th power. Okay? And we're done. We can figure out what 1/3 to the 4th power is. It's really 1 over 3 raised to the 4th power, whatever that is, 27 times 3, which is 74, I think. Nope, not even close. It's not even close. It's 81. 600. Mental arithmetic and mathematics are not the same. If they were, I would be terrible at math and I wouldn't be your professor. Any questions so far? Very good. I like the responses. Okay. All right, moving on. Let's solve radical equations. What's a radical equation? Well, it's an equation that involves a radical and some x's. Solve for x here. Square root of x minus 1 is equal to 3. What is x? Well, I sure can't solve for x while it's inside that radical. But I can remove the radical by doing what to both sides? This is a square root. So to undo a square root, I'll raise both sides of the equation to the 2nd power. So it undoes the root, and I get a 3 squared, which is a 9 over here. And so x is merely just 9 plus 1. Let's do another example. What about the square root of 2x minus 3 minus 1 is equal to 7? How do I solve for x? Well, the answer is not to square both sides yet. Why? That pesky number 1. That minus 1 there, we got to get rid of it, because if we square both sides, then we'd be squaring the quantity square root of 2x minus 3 minus 1, and then you would have to FOIL, and that's not what you want. You have to distribute. That's not what you want. What you want to do is make it simple. So we add 1 to both sides. Prior to doing that, this becomes an 8. And now you can square both sides. So now I get this, what's inside the radical is equal to 8 squared, which is 64. 600. When then I add a 3 to both sides, I get 2x is equal to 67. And then I divide both sides by 2, so I get x is equal to 67 over 2, which equals 200. No, it doesn't. I'm just kidding. This is an inside joke with me and my wife. Make it sense so far?
About like big bench press and not cardio.
What happened?
Because he has that big belly.
Hello?
Big.
Who's talking right now? Who is talking right now? Someone needs to either ask a question or remute themselves. Audrey, your mic is on. I think they accidentally unmuted. Audrey, I'm gonna mute you, Audrey, unless you have a question. Audrey Dunn, do you have a question? Okay. I heard something about bench pressing and cardio. Okay. So, moving on. What if we have a situation where, unlike this situation where we have just one radical, what if we had two radicals? What if I had the square root of x minus 1 plus the square root of x plus 1 is equal to 2? How do I solve this one? Well, actually now you do have to quote unquote FOIL because you have no options. There's no other choice. Before we had a choice. We added that 1 and just square rooted to get rid of the radical. Here, we don't have a choice. There's really nothing we can do. We have to square both sides right off the bat to get rid of some radicals here. So this side becomes a 4 because 2 squared is 4. This side is just it times itself. So really, we have this square root of x minus 1 plus square root of x plus 1 squared, right? So let us FOIL or distribute, if you will. I'm going to distribute. So I get square root of x minus 1 times itself, times this quantity. Square root of x minus 1 plus square root of x plus 1. All right? Plus square root of x plus 1 times square root of x minus 1 plus square root of x plus 1. Right? This is just FOILing. But now we're doing distribution. It's the same thing, okay? So square root of x minus 1 times square root of x minus 1 is just x minus 1. Square root of x minus 1 times square root of x plus 1 gives me square root of x minus 1 square root of x plus 1. Then square root of x plus 1 times square root of x minus 1 gives me square root of x plus 1 square root of x minus 1. Then square root of x plus 1 times square root of x plus 1 gives me that's x plus 1. And recall this all equals 4. Okay. Notice that this minus 1 over here and this positive 1 over here cancel. And then these x's can combine here. So moving the calculation up here, I get 2x. And then there's 2 of these terms plus 2 of these terms. Square root of x minus 1 square root of x plus 1 is equal to 4. Now what? What are we going to do? Well, notice that we can factor out a 2 out of each of these terms. Dividing both sides by 2, this side becomes a 2 because 4 over 2 is 2. And this becomes x plus square root of x minus 1, square root of x plus 1. So what do we do now? We still don't know what x is. What do we do now? Cry? No. No. Let's clear up some more space here. No. We don't cry. Even though there's nothing wrong with crying. But usually, if you're just crying, that means you're defeated and you're giving up. My students will never give up and never be defeated. So you can cry if you want, but you need to be crying all the while fighting. Tears coming down your eyes, but you're still fighting. Why doesn't the powers cancel out the roots like before? Oh, because it just doesn't. Joseph, it just doesn't. Because before, we had like x minus 1 is equal to 2, and we squared both sides, radical goes away, and then we solve for x. And everything was nice and dandy, but now it's not true, because unlike this, when it had one radical, we had a sum of radicals. Our problem was, what is x plus 1 radical plus x minus 1 radical? What is it when we set it equal to 2? What is x? That was our original problem. So just squaring both sides doesn't get rid of the radicals because of the middle term had a radical. The last terms, when this is multiplied times itself, gave me my x plus 1. And when this was multiplied times itself, gave me my x minus 1. But the combination of the two, this times that, the radicals don't cancel. I don't like that answer. I don't get how I can help you. What do you mean? The reason the roots don't cancel is because they just don't. You know, square root of x plus 1, if I multiply it times the square root of x plus 1, only then does that equal what's inside the root, because that's square root of x plus 1 quantity squared. But if they're different, if you have square root of x plus 1 times square root of x minus 1, that can't happen. They're not the same. That's why. Okay, but we're not done. We're not done because I can subtract the x from both sides here. We don't cry. We think about what we can do. And I just said crying is okay. I mean it. Crying is okay. If you want to cry, do it while fighting. So we get this situation. Notice that from a long time ago, the square root of some m times an n is the same thing as square root of m times square root of n. So clearly, if this is true, we can go in reverse. Meaning, I can express this left-hand side as this. Okay, so this is a great step to do because now I can square both sides. And now it's all under the same radical, so that radical can get squared and the radical will go away. So then I get this is x minus 1 times x plus 1 is equal to my quantity 2 minus x squared. So it seems like things are getting better, and they are because there's no more radicals. We can solve for x now once we FOIL both sides of this equation. So this gives me x squared plus x minus 1. And this gives me 4 minus 2x plus x squared. So these terms cancel, so I just get x squared minus 1 over here. And this becomes a x squared minus 4x plus a 4. Very good. This is very good here, because notice that I can subtract the x squared from both sides, and they cancel. So I get negative 1 is equal to negative 4x plus a 4. Notice that I can subtract the 4 from both sides, and I get a negative 5 over here. That's equal to my negative 4x. And guess what? We can stab the problem in the heart and finish it off by saying that this is a negative 5 divided by a negative 4, which is just positive 5 over 4, which is my x. Now, how do you like it, Joseph? That's a lot of steps. Yeah. That's why mathematics, it's important to not memorize in mathematics. It's important to understand. Because if you understand, then the steps are just logical, step-by-step processes that you make in your head. Whereas if you have to memorize, that's a lot of steps if you're going to memorize every step. But if you understand, you can start at the beginning, then work your way to the next step through using logical reasoning, then and mathematical critical thinking. Then you can move to the next step, then to the next step, then to the next step. Then once you're done, you realize that there was a lot of steps, but you figured out the answer. So that's really all that matters. In mathematics, it's important to just really make sure that you understand instead of trying to memorize everything. That is why mathematics is different than most subjects. Because let's say biology, they just say, here's a cell, here's a mitochondria, here's an endoplasmic reticulum, here's a ribosome, here's an anticodon. A pheochromocytoma is a micro tumor in the adrenal medulla that secretes epinephrine randomly. These are all things you memorize. But in math, 6 minutes. Thank you, Isaac. In math, it's you have some fundamental things that you have to memorize, but the rest is you just freestyle. Math is like freestyling. You just freestyle it. So what about, we'll do one more radical problem with 2 radicals. How about square root of 3x plus 7? And it's something that, math is a skill. It's okay if you're not fully efficient at that skill, you know? Nobody popped out the womb knowing how to ride a bike. You had to practice. So once you practice, you'll realize that, yeah, it's a lot of steps, but it really wasn't that bad. Let's try to solve this radical equation, okay? So again, there's no constant terms we can send. We are forced to square this thing. We have no choice. 1 squared is 1, and now we have to square this thing. So this thing times itself is 3x plus 7. This thing times that is root 3x plus 7, square root of x plus 2. And then you do it again. So I'll put a 2 up here. And then you multiply this times itself to get this x plus 2. Then we combine like terms, this 3x here and this x here give me a 4x. This 7 here and this 2 here give me a 9. Plus my 2 square root of 3x plus 7 square root of x plus 2 is equal to 1. Okay. So then I can send that 9 packing to the other side of the equation. Actually, I'll send that 4x over as well. So I'll get 2 square root of 3x plus 7 square root of x plus 2 is equal to negative 8 minus 4x. When I subtract the 9, it becomes a negative 8, and then there's my negative 4x there. Then what I can do is I can divide both sides by 2. Bring the calculation over here. This becomes a negative 4 minus 2x is equal to the square root of 3x plus 7 times the square root of x plus 2. Okay. Then we realize that this is the same thing as negative 4 minus 2x, which is equal to the square root of the quantity 3x plus 7 times the quantity x plus 2. Then we realize that now is the time to square both sides again, because now the radical on the right-hand side will go away. And over here, I would get a negative 2x minus 4 quantity squared is equal to 3x plus 7 times x plus 2. So then notice this becomes negative 4, or no, this times itself is 4x squared. That times that is a positive 8x. That times that is a positive 8x. This times itself is a positive 16. Okay. Then over here, 3x times x is 3x squared. 3x times x is 3x squared. 3x times 2 is 6x. 7 times x is 7x. 7 times 2 is 14. So then we combine like terms. This is 4x squared plus 16x plus 16, which is equal to 3x squared plus 13x plus a 14. Okay. So now we combine like terms. Subtracting the 3x from both sides, I just get an x squared here. Goodbye, goodbye. Subtracting a 13x from both sides, I just get a 3x from here. Goodbye, goodbye. Subtracting a 14 from both sides, I just get a 2 here. Goodbye, goodbye, and this is a 0. And now it's just this following equation. What's 2 numbers that add to give me 3, but multiply to give me 2? You guessed it, 2 and 1. 2 plus 1 is 3. 2 times 1 is 2. So that we just factored that sucker. So now using the 0 product rule, this implies I get x plus 2 is equal to 0, and my x plus 1